Thank you very much. So I will explain you a few things before we start the virtual tour. It's a premiere for me, so I hope everything will be all right. So this is the actual site of, it's a power-to-gas site called Jupiter 1000. It's a common project, a common interest project we have with 9 partners. We work very hard to build this project, and we are really proud to present today this project. So first, a few words for my company. I work in GRTgaz, which is the main transmission system operator in France. So you have some figures here. I don't need to explain in detail, but we have a very large high-pressure pipeline network. So we are actually very much involved in the energy transition because, as you know, today we transport more or less 2% of renewable gases. Most of them is a fossil fuel, and so we have to make the balance the opposite very quickly. So we were involved in the changing of origin for gas, and as a matter of fact, we have also we were interested in the possibility that we have to address the storage of energy with the power-to-gas system. I don't know if some of you know something about power-to-gas, but simply it's the way to transform energy into gas. And energy coming from, if this energy comes from electrical renewable, we will have renewable gases, and we can address some very interesting things. So why, you can ask yourself, why is GRTgaz involved in power-to-gas? I try to explain it, but first of all for us is we need to decarbonize our grid and to replace the fossil fuel with renewable fuel. So that's a goal we are seeking, and there is many. Oh yes, I could do with that.
The pointer. You need the pointer. Yeah.
And yes.
And I think you can move also. So
okay.
The pointer is there. Okay.
Okay. Okay. So that's the first goal for us, decarbonize our grid. But it's also a matter of how we can connect a power grid with a gas grid. And power-to-gas is a way to do that. And there is some value to do that because you can store gas much more better than you can store electricity. And that's the way to do that. And you will see it's not very complicated technology. I mean, we are speaking about electrolysing. We are speaking about methanations, which is, by the way, a little bit complicated than electrolyzer. But what we have done here in Jupiter 1000 is to put those technologies together and try to make them work the way we wanted them to work. And the way we wanted them to work is to take advantage of the price signal of electricity. You know that when actually when there is a lot of renewable electricity made of solar or wind turbine, the main problem with those kind of energy is that they are not predictable. So you have wind when you have wind, and you have sun when you have sun. If you want power when there is no wind or sun, there is no power. And at the opposite, if you have too much wind or too much sun, the energy is lost. So the main purpose of this installation is to take advantage of those surplus in energy and take them and convert them into gas. So that's what we've done. And it's also a way to work with in the area of Fos-Marseille, which is a very special place for energy because it's you have the harbor, you have a lot of infrastructure in energy, and I will come again on that at the end, but it's a very special place for us. So, non, ça marche pas. Ok. Non, mais ça va aller. Ouais, je vais le faire comme ça. So these are the chemical reaction we deal with. Very simple, electrolysis and methanation. So we need power and renewable power. We need water, and we need CO2. Quite simple, in fact. Quite simple, but how to do it the good way for us to offer a gas power storage for both the systems. That's the difficulty. So the main goals of this demonstrator is to validate, as I said, the technology, experiment also hydrogen injection in the gas grid. At the time we started this project, it was in 2015. Our idea was to inject hydrogen into the gas network. Now we move a little bit from that, and with the need for industry to have a lot of hydrogen, we think it should be better to have a dedicated hydrogen network built all around Europe, or in France especially. But at that time, when we launched this project, our idea was to inject hydrogen into the gas grid and then confirm the flexibility we could offer to the power grid. It was also the first project of that kind in France, and one of the first in Europe. And finally, we wanted to explore which business model we could have for such a technology, because at that time and nowadays, I must say it's not a technology. You can build plants like that, but you will not make a lot of money with that. The business model is to be confirmed by a lot of things. I will explain that later. I told you we work very hard to build this collaboration with our partners. Here are our partners on these schemes, and first of all, we need some power. So the power is made by CNR. It's a renewable power, and we have some wind turbines just around the port of Fos-Marseille. But the energy could come from all the France. We work also with RTE, which is a power grid operator in France, because we need very close analysis together to be in order to be efficient when we want to compare our data with their data. So it's very exciting because we don't used to work like that before, and it was something very interesting, promising, because we believe very strongly that we have some good project to build tomorrow with the cooperation of the two grids. Then for the electrolysis, we chose two different technology, alkaline and PEM. I not said that, but Jupiter 1000, why this name? Because Jupiter has got a lot of hydrogen. It's a planet with a lot of hydrogen, and 1000 is the power of the two electrolysers split in half thousands. So they were provided by McPhee. And then in order to have methane, we need CO2 to do the methanation reaction. So we chose to capture CO2 on iron unit not very close to the site, and we take CO2 on this site, and we built a network to bring them to the main site. And then we could inject the hydrogen into the grid, or make the methanation process in order to inject the synthetic methane into the grid. So we have the choice, and we have to. We wanted to play with this tool, so that's what we done, and it's still in work in progress now. Okay. The methanation reaction is made by Chimod, which is a spin-off of the CEA. And they have a very special way to do that, and it's very interesting. And then we have the product, we could inject them in the grid. The site is located in the Marseille Fos Harbor, and you have the figures of the demonstrator. So we enter 1,000 watts of electricity, and then we could have 200 cubic meter of hydrogen, or if we do the transformation with one electrolyzer, we could have 25 cubic meter of synthetic methane. This project is working for three years in order to get the result we expect, and then we will stop it, or most probably we are on thinking of what we could do with those electrolyzer and methanation process, etc. And we hope we could find new partners to make this project go further even. So this is a view of the site, and we will go for the virtual tour very soon. So you can see, I will not explain, I will explain with the virtual tour, it would be easier. This is the one view of the harbor. One thing important to have in mind is that we are connecting to the gas grid. When we inject synthetic methane or hydrogen, these molecules are used by industrial customers. So we were very careful with that, and we make a working team with industrial, asking them if we could do that, and how we could prevent them from disturbing their process. And it was very interesting also because they were enthusiastic about that, and we worked together very well to see if there was problem. And as far as we know, there were no problem because the 200 cubic meter of hydrogen in the network, it's not very much hydrogen if you compare to all the natural gas flowing into the pipe. So it's about 2 or 3 until 4% of the flow you have in hydrogen, depending on the consumption of the network. So it's not a big deal, but it could be. And so we have to check with the industrial customer whether or not there are some problem with that molecule, because, for example, when you inject hydrogen in a gas network, you make I don't know how to say that in English, PCS, PCI. It's the power calorifique. Yes, the calorific power, it's going down, and most of the customers are using natural gas as an energetic vector, so they need energy. So it could be a problem if you have much more than 4% of hydrogen, but in this case it was okay. So this is a synthetic, okay, just to explain, this is yes, okay. For the CO2 network, this is Ascometal, the customer we have produce iron here, and we build this network going to the site with the CO2 for purpose. So it was a 1 or 2 kilometer network. We have to build it. And once again, it was a good experiment for us because we don't use to build a CO2 network. So it was very interesting also.
Don't use this one. Quand vous êtes près des autres,
okay. Okay. So, how many time left?
You still have 32 minutes before reaching 50. Donc vous avez encore 32 minutes avant d'arriver à 50.
Okay. Okay. Thank you. Okay. So this we are going to see it on the virtual tour, but this is a picture of the main electrolyzer. So we have two electrolysers, the alkaline one and the PEM, which is much more smaller. And what we wanted to check with this equipment is how quick they could start and stop. Because most of the time when you buy those products, people who are using it are using like in a flat way. You don't need to make some modulation with it. And the purpose of this demonstrator is especially to have start and stop. And so we were very interesting to know how those kind of electrolyzer will work on those conditions. And the PEM electrolyzer are supposed to be more friendly with start and stop process. And what we found is that it's not often the case, because they need to when they stop, they need to have a minimum of temperature, so special condition, so that which the alkaline don't have. So when you stop the two, yes, the PEM is going faster to climb, to ramp up, But if you take all the parameters in account, the difference is not so important. So that's one of the results we are going to let people know, is that those kind of differences are not so big as we expected. So this is the site. What were our main objective? As I said, it was learning about power to gas and about hydrogen, because before that, GRTgaz, my company, doesn't deal with hydrogen, and we believe strongly that it would be an energetic vector in the close future. Now we have some project on a European basis for building a network of hydrogen, and it was a good way to start with this technology. And also, as I said, propose the power to gas as a storage for the energy system. And with the knowledge we wanted to have of those technology, came all the measurement stuff we have to do, all the security around hydrogen, which is very important. And as you may know, the hydrogen network exists already, but there are not so much in the world, and in Europe, I think it's 1,000 and something kilometers of hydrogen we have. So it's not very much. Keep in mind that only the French network is 32,000 kilometers. So it's not the same scale. So surely we need to learn a lot of things before having such an infrastructure which can bring us to the decarbonization. Okay, so I propose to go to the virtual tour now. So this is the site you already seen on the slide. And we are moving like that. So if you were on the site, you enter this way. And first of all, I will present you the electrolyser. So these are the electrolyser. Oops. It's not working, not working, up, working. So left and right, the two we have. So this is the stack of the, and it's really what you see, what you could see if you were on the site. It's very close to this view. And this is all you can see the stack of the electrolyser, and then the two reservoirs for hydrogen and oxygen. I must say that for this experimentation, the oxygen is released to the atmosphere, but in our calculation, the calculation we made, we make after that, we can take value for this oxygen because some chemical industrial need it very well, and that's part of this optimization we have to do in order to have a business model that could work tomorrow. So now the hydrogen is kept for methanation and injection, but oxygen is not. So this is what we can see. Up. And the other stack, this is the PEM electrolyzer, proton exchange membrane, if you wonder what it is. And one thing interesting is that in order to work, this kind of PEM electrolyzer needs very pure water. So we have just here, I think, look up, a first facility. No, so it's the back of the alkaline electrolyzer, sorry. Should be this one. No. So I open all the doors. It's not this one. Okay, I think it's this one. Yes, it's water processing. This installation is common for the two electrolyzers, but it's very rough processing. So in order to make for the alkaline one, this one is okay. It's a very classical processing, but we need to go further for the PEM because of the need of much more pure water. So we have a special processing for that, which is called ultrafiltration, in order to have very pure water. So we've got the two electrolyzers here. And we need also to have direct current to make it work, because I don't tell you, but it's working on direct current. So we take the input voltage of 20 kilovolts and we transform it into 100 volt direct current. Okay, this is for the electrolyzer. This is the power, the same thing. It's exactly the same. So, okay. So now we have our electrolyzer and we have hydrogen. So what do? We are there is a storage. Maybe yes. There is storage, and then we go with the hydrogen. If you wanted, we want to make synthetic methane, we have to take advantage of the CO2 coming by the network, I told you, and then we go to we go to the methanation unit. Ouais, je l'ai là. Vous avez une prise quelque part? Oui, on va enlever l'autre. Ouais. Ah oui, là, moi, je peux faire des bêtises. Ouais, là, ça va être un peu compliqué. On va faire des bêtises. Alors, je crois que celui-là, on va le mettre à la place de celui-là. Ça, je crois que c'est l'ordi. Ouais. Ça, c'est l'ordi. OK. On va mettre le vôtre. Sorry for that. Ouais, it's running out of... Qu'est-ce que j'ai fait? Ah. No, sorry. It's okay? It was real again. I don't know. Maybe. It's strange because I was quite full. Maybe. Yes, it was. It was really kaput. So. Have to wait. Je pense que c'était vraiment la batterie du monsieur qui était d'accord. Je pense aussi. Voilà, ça y est. Là, normalement, c'est reparti. Ah oui, il s'était sauvegardé. OK. C'est reparti. Merci. Voilà. OK. can't go to the methanation unit. That's a shame. Excuse me. So, maybe got a problem with this. I will try again. And if not, yes, I think the computer is working, but not so as fast as I wanted. So let's, if it doesn't work. Okay, I'm going to explain you.
Peut-être que vous le redémarriez.
Je sais pas. Zut, ça c'est dommage. Ouais, je vais essayer de le redémarrer. So what as it's working, I wanted to tell you that the methanation reaction is a reaction which is very exothermic. So as we put together the CO2 and the hydrogen, it produces a lot of heat, and the control of that heat is one of the most important parameters we have to deal with, because if the reaction go too fast, we have to stop it, because it would make everything melt. So that's the one interesting thing to know about methanation. Let's see if we were lucky or not with this methanation. Yes, okay. We have two skins, you can see, two skins of exchanger, which is the main thing we have, and then you have the hydrogen coming from those pipes here into this block, which is one of the exchanger of key mode, and the other is here. And when the reaction is over, we have to dry the synthetic methane in order to expulse the water, because you have the reaction, but there is water as a byproduct. Yes, it's interesting to know that this heat could be one part of the optimization we could make of this process, because we could, for example, use this heat on other process on the site, and if we have high temperature electrolyzer, for example, which is a new technology for electrolyzing, we could use that heat produced here and transport it to the electrolyzer of that kind, and it could be a good loop to save to make all the process more efficient. So this is the methanation, and it's a very compact one, which is not always the case, and it's a container, je sais pas comment on dit en anglais. A tank, yes. So you can see it. It's very compact. then we could compress this synthetic methane in order to inject in the grid. We can see here on this view the CO2 coming from the Ascometal plant. We have a little storage of CO2, and we need to compress it in 30 bar. That's it, the level of pressure we need to work. And so we have our two products, hydrogen and synthetic methane, and then we could inject them as we want on the grid. So this is a view of the injection facility we have. We have to blend all the hydrogen with the natural gas in a way there is no kind of bubble of hydrogen in the network, because as I told you, it could be a problem for the customer. So we make it make it that way with those kind of equipment, and we have to be very careful not to interrupt the gas flow. So this is all the purpose of this piece of equipment is to inject all the products we wanted, and not disturb all the customer around this site. It's very simple to say like that, but it's not so simple to do it. We can see here on the back the hydrogen pipe, which are very thin compared to the natural gas one, which are here. And then the other part of it is the bypass of the system in order to preserve the gas flow for the customer. Okay. One other last thing I wanted to show you is no, not that. Where is it? Okay. It's a lab we have made for this facility because we need a lot of data for this this process. So we built this analysis laboratory, and we've got all the gases we take it in order to characterize them on the chromatograph and so on. And we've got a lot of analyzer. So it's it's not in English. But you can see it's a mass spectrogram. Okay, and that's what I wanted to show you this morning. This Jupiter 1000 site, which is, by the way, this is the wall of all the partners we have, and this demonstrator was built with the concours of the European community and the French ADEME, which is the Agence de Transition Écologique in France. So, thank you, and if you have some question, I will answer it if you want.
Thanks a lot.